Welcome to this lecture video on electric potential. The first thing to know about electric potential is that potential is not the same as potential energy, right? So they're closely related and we'll see how. But when somebody says potential, it means something different from when they say potential energy. That is confusing terminology. I'm totally with you on that, but this is something we have to be aware of. So you may remember from a long time ago a video that I said might be more of a reference video where I introduced this map of electromagnetism. So here is that very same map again. It looked very, very complicated, but by now we've sort of covered a whole bunch of the concepts, right? We talked about the force and Coulomb's law, right, what charges do. We talked about electric field as sort of the, with this relationship here, it's the force per coulomb that you put somewhere, and then calculate with Gauss's law, so on and so forth. Now we've talked about, very recently, about potential energy and the relationship between the potential energy and the force. Potential energy exists because electrostatic forces are conservative. And so now we're moving to this last kind of the fourth corner of this map. And the key thing to understand, to not get confused about those four concepts, is understand that essentially electric field is to force what potential is to potential energy. Electric field is the force on a hypothetical coulomb of charge you put somewhere, while potential is sort of the potential energy of a hypothetical coulomb that you put somewhere in the presence of some other charges. So if you remember watching this video, being horribly confused, maybe you turn it off halfway through, well, after this video might be a good time to go back to it, because by now you'll be able to make sense of pretty much everything that you can see on this map. Alright, but let's talk about what electric potential itself is. So here's a scenario. Imagine this. Imagine I've got a couple of charges, maybe make it 4 charges, A, B, C, D. Could be, 100 charges. It could be continuous charges, a rod of charge, a disk of charge. Doesn't matter what it is. And now let's imagine I have some other charge here. Let's call it this little Q, charge Q. And I want to move this charge to this spot right here. Right? And I might move it by one path or a different path, but because it's a conservative force, electrostatic forces, it doesn't really matter what path I pick. I have to move it from really far away to this point right here. Now before I move this charge over here, these 4 charges, right, they have a certain amount of potential energy, just the configuration of those 4, because they're going to be, interacting with each other, and you can count there's going to be 1, 2, 3, 4, 5, 6 different combinations, AB, AC, AD, BC, BD, and CD, right, like you can draw 6 different lines between them. But whatever that potential energy is that those have amongst themselves, we don't care because we assume they're going to stay in place. So whatever they have, it's not going to change. It doesn't affect anything else. What we care about is, well, what's the change in potential energy if I move the charge from far away to over here? So far away, like over here, right, far away, the potential energy associated with this charge here is 0. Right? Hopefully remember that from the potential energy lecture, just because you divide by R, and is large, large, large. So all the potential energy terms are essentially very, very small, approximately 0, because the distance of this charge to any of those is approximately infinity. Practice just is very large compared to other quantities. But now as we're moving it over here, and by the time it gets here, this charge has gained or lost, depending on the sign of those charges, some potential energy. And the way I'd calculate that is I'll just add up those 4 new interactions. 1, 2, 3, 4. Each of those interacts with the one that I brought here. So the change in potential energy due to moving the charge Q to here, and doesn't matter what path I take, is going to be, let's call this RA, RB, RC, and RD. It's going to be K QA times Q over RA, right? From here, it's gone. It was 0 here. Now it's this. I'm going to add to it k qb times q over rb. I'm going to add to it the potential energy due to the third interaction, k qc times q over rd. And I'm going to add to the c. What am I doing? Add the last one, k qd times q over rd. Right. So each of them was 0 here. Well, now that's some finite value that I can calculate, knowing the charge qa, qb, qc, qd, how many coulombs, and then the charge of this one, which I just call q. So I can write this, and we can just factorize out the q, the charge of this one, because this is involved in all of those interactions. And I could take the k out too, I'm not going to. qa, ka, qa over ra plus k qb over rb plus k qc over rc plus k qd over rd. You could imagine if I had more, this would just keep going. More charges here. If I had a continuous charge, like a rod of charge or a disk of charge, then those expressions would look different. Right, we worked out what electric field is for a disk, for a rod, and so on. So we'd be working with those instead. But the idea would be the same. In all of those potential energies are proportional to the charge that's being moved. So I can take this one out. The q comes out front. Now, I could imagine I put 1 coulomb there. I could imagine I put 2 coulombs there. I could imagine I put 100 coulombs there. Doesn't matter what I pick. It's just going to appear up here. So this expression here is essentially the delta PE, the change in potential energy per coulomb that I've moved from far away to over here. Right. And this, so the units of this part would be in joules per coulomb. And this thing here, right, the potential energy per coulomb is the thing I'm going to call the potential. Right, so this thing I'm going to call the potential, not the potential energy, just the potential. So potential at this point, or the potential difference between far away and this point. What's the change in potential energy? So really I should be more careful when I call this the potential or the potential difference relative to infinity, being really far away. And most of the time we're going to care about calculating potential differences between 2 points, a bit like calculating the difference in potential energy between 2 points as an object moves from one point to another point. Now we're going to give the potential the symbol V. V stands for voltage, and it's another term for potential. And voltage in particular is used in the context of electric circuits, which we're going to come to in just a little bit. Notice though, there's this analogy that I kind of hinted at when we're looking at the map, right? We have that the electric field is the force per coulomb, or force per charge. We could use any other units. The force per charge. Of course, the force, you have to understand it. The force on an object that's moving, maybe in the presence of other charges that create electric field and so on, right? But the force per coulomb. Similarly, the potential is the potential energy per charge. Right? So I add one charge to some configuration. Well, by how much does the potential energy change? Well, the potential is that quantity per charge that has been added. The electric field and the potential, they're defined at every point in space, right? So in my example from before, there's the potential at this point is defined whether or not I actually move a charge there. If I move a charge there, I can calculate the potential energy that has been gained or lost. But without actually doing this, you can imagine at any point I can pick, there's a well-defined potential. What would be the potential energy gained if I brought a new charge to this point? It was the same idea with electric field, right? At every point in space, I can ask, well, what would be the force on a charge that I brought to this, that I put at this point. So this is it's exactly analogous, and hence these sort of four corners of the map, if you like. Now there's an analogy here that we can make for potential and potential energy. So imagine you're climbing a mountain, right? So this analogy, and we're going to do analogy with gravity. In this case, gravity on a planet. So imagine that there's some sort of mountainscape. I'm going to draw it from the side, right? And you start down here. There's a little sort of in smoke coming out, right? You'll set out on your hike, and you start here, and you end up at the top of the hill. Now you've gained some change in height, a certain amount of potential energy. In this case, gravitational potential energy, right? Namely, your mass times g times the change in height. Went up that far, well, you've gained that much potential energy. But the hill is just what it is. The hill doesn't care who goes up it. How heavy are you? Doesn't affect the shape of the hill or how high the hill is. So we can talk about the gravitational potential, not potential energy, or the gravitational potential, difference, because it's the difference between the bottom and the top. And that would be the gravitational potential energy gained per mass, right? So, for example, per kilogram that I move up there. If I take a backpack with 10 kilograms and I go from here to here, well, how much potential energy has this 10 kilogram backpack gained? Well, I can find out, right, using this expression, but I can also just ask, well, how much potential energy do I get per kilogram that I bring up the hill? And that is my gravitational potential difference. And that's exactly analogous to the idea of the electrostatic potential and electrostatic potential difference. And so what we can do now is we can make this abstraction, namely that we don't care about what the source charges are or where they're located, what shape they have. We just care about potential difference. The same way we were able to talk about the electric field and its effects without necessarily knowing what caused the electric field to be there in the first place. Let's use an example that sort of does that. A grain of dust, and you put a mass of the dust, 0.1 grams, I think it's a very big chunky grain of dust, and the charge of the dust particle, we imagine it's charged, it's plus 1.0 nanocoulombs. It travels across a potential difference of minus 8 volts. So it travels down the potential hill. The analogous thing would be it travels down the hill, not on the side of the mountain. It's starting from rest. How fast will it move? So let's figure that one out. So initially, let's say it's over here. I don't know where it is. I don't know what distance it travels, but let's imagine we start here. So here, its kinetic energy is 0. It starts from rest. It travels, I don't care along what path. Doesn't say it's a straight line, doesn't tell me how long it takes, but it knows so somewhere from up here to down here, there's a potential difference, delta V, so potential difference, change in potential, that is going to be minus 8 volts. Now, this is really, really annoying, right? Volts, V, is the unit of voltage or of potential. So it's V for potential, the quantity itself, delta V more often than not, but also V for the unit. And if you print it, and I can print, this would be in italics because it's a variable. This would be not in italics because it's, you know, a unit. But when you do it on paper, it's hard to distinguish the two. So you sort of just have to either know from the context, this is minus 8 volts, or you have to, you know, always work with delta V's and never with just V's. It's just a nuisance, but we can handle it because what matters is that we understand what we're doing. Or you could just write PD for potential difference. Totally fine. So what we know is to starting from here, going to here, no matter what path we take, it's an 8 volt potential difference down the potential hill, right? Minus. So it's 100 volts here, 92 volts here. 1000 volts here, 992 volts there. Minus 6 volts here, minus 14 volts here. Doesn't matter what the values are, I know the difference is 8. This is 8 higher than this, because as I go this way, I go down by 8. So that implies, the particle goes from here to here, the potential energy, the change in potential energy, delta PE, is the charge of the thing that's moving times the potential difference, because that's the potential energy change per charge. So how much charge do I have? Well, I multiply those. So that's going to give me minus 8 times this, which is 1 times 10 to the minus 9. So this is going to be the potential energy gained is minus 8 times 10 to the minus 9 joules. In other words, i.e. it est 8 times 10 to the minus 9 joules of potential energy have been lost. Well, they haven't been lost to nothing, right? Lost meaning they have been converted to kinetic energy. Well, so what do I have? Since I have initially 0 kinetic energy, I have 1/2 m dust v, let's call it final, squared for final, that's equal to 8 times 10 to the minus 9 joules. Because we lost that much potential energy, so we've gained that much. How did we calculate that? We took the charge of the particle multiplied by the potential difference. We know what this one is. This is 1 times 10 to the minus 4 kilogram. Make sure you convert to kilograms. And so we're going to get that V final squared is, I take this to the side, this to the side. We're going to get 16 times 10 to the minus, what does this make? 4 minus 5. And then I have to take the square root. And I think that comes to 0.00126. I want to say meters per second. That is working in joules. And a joule, remember, a joule is nothing but a kilogram meter squared per second squared. So I counted kilograms. This is in meters squared per second squared. This is in meters per second. And we've solved it. Now just quickly summarize again. Force, right? You calculate the force between two charges. Well, the force on a charge per amount of charge is the electric field. It's one way to characterize the electric field. Similarly, the potential energy, or the potential energy difference per amount of charge, let's move this from one place to another, that's called the potential difference. Right? The potential is the potential energy per charge put at a particular point. Those two, right, they're related essentially via the notion of the work done, or I can write that the force is minus the slope of the potential energy. Now what variable do I put here depends on how you characterize your system. I'm just going to put R, but you know, it depends, X, Y, Z. And so similarly, there's the relationship over here that says that the electric field is the force in the R direction. The R direction could be X, could be Y, could be Z, could be some other variable that you're using, is minus dV, the R in this case, right? So it's kind of the downhill slope of the potential gives you back the electric field. I guess it's kind of going both ways. Good. Again, this is essentially the big map I showed you, and you might want to go back to it now. But just the key ideas sort of distilled that shows the relationship between those four quantities. What if I want to go the other way? What if I want to find the potential or potential difference from the electric field? Well, I can write it like this. Delta V is minus the integral of the electric field along some path. So this is the path integral because I want to find the potential difference between here and here. If you actually want to use the electric field, you have to decide what path are you going to take to go from one spot to the other. Your answer is not going to depend on what path you take. You take this path, you take this path, but to actually evaluate this this expression, this integral, you have to pick a path, and maybe the straight path is the easiest one to calculate. It doesn't matter because it's a conservative force. That's why that thing exists, right? Because it's only a matter of which 2 points are you comparing. But to calculate it, you need to add up the sort of potential electric field strength times little step. We make an analogy, I think it helps clarifying the meaning of this. Let's go back to our hiker that's hiking up the mountain, right? We started out here. Here was our little inn where we started out in the morning. And we're going to hike up the hill. Now let's just think a bit 3D here. If I'm going to start out here. Here's me, the size of a house, I know. And I could choose, and I want to end up here. I want to measure the height of the hill. And maybe I can't just sort of measure it by eye from below. It's hard to do. So what I could do is I could say, okay, every step I take, I'm going to measure how high that step takes me. So here I'm flat, and I start going up the hill. And every step I take, I'm measuring the height difference, and I'm going to add them all up. And maybe this is the path. Well, that'll give me some answer, and then I've calculated the height of the hill, or alternatively, the amount of potential energy that I've gained, or the potential energy per kilogram, right? Just by measuring the height difference for each steps and adding up those height differences. But I could also have gone to that point via a different path. Maybe when it goes a little bit further down first, then up in front of the mountain, then maybe it goes down again, and it's a pretty way around, and I'm going to approach the peak from up here. My calculation to get to this point would be different because I go down a bit, I go up, each step is different than the steps along this path. But no matter what path I took, if I do my calculation, my measurements right, I should end up calculating the same height difference, or the same height of the mountain. And that's exactly what we're imagining we're doing, but with electric potential steps, rather than electric fields. So really what I'd be doing here is I'd measure how steep is the mountain, how big a step do I take. That allows me to calculate the height difference. That's evaluating this for one little step. And then I'm going to add up all my steps, and if I add up in this way, or add up this way, or add up this way, either way it should come to the same final potential difference between here and there. So this analogy hopefully helps clarify that. Let's just finish off by doing 2 quick examples. Here's my first example. I imagine I've got 2 metal plates and I charge them up. So this one carries a positive charge, this one carries a negative charge, right? And they're really big compared to, they keep going compared to how far they are apart. So like two metal sheets held really close to each other, a small gap in between. I imagine the gap is 0.02 meters, essentially 2 centimeters. So because there are all these positive charges here, negative charges over there, there's an electric field, that the field lines come out of the positive charges, go into the negative charges. We know what the field due to a plate, what that looks like. So between those plates, we're going to get just constant electric field from left to right, from positive to negative. And I imagine that the electric field strength everywhere in this space is 100 newtons per coulomb. So I want to figure out what's the potential difference between those 2 plates. Well, let's do the calculation. delta V, I mean from this point to this point, is equal to minus the integral of the electric field. So the path integral, right? Going along some chosen path and adding them up. Well, we've got to be specific. Let's pick a path. Now, you could do this picking any path. If you pick a diagonal path, it's going to be longer than a straight path, but every step is going to take you down the potential hill by a smaller distance. Let's make our lives easy. Let's pick the straight path, right? So the path I'm going to pick, I'm going to start here, and I'm going to go over there in a straight line. That's the path I'm going to choose to integrate along for obvious reasons, because it's the simplest one. Right. So we're going to pick, I'm going to circle in purple because I do this in purple. Right. So now let's write down what this is explicitly in terms of our chosen path. Well, minus is minus. Now my integration variable, well, I could just label this point x equals 0. And then this x equals something. Okay, so it goes to, well, here it would be x equals 0.02 meters. Right? Because that's far away, and I just chose my axis along that path. Makes my life easy. So what's the electric field? Well, the electric field is going to be 100 newtons per coulomb. Then I take small steps, and the steps are going to be a size dx, right? Little dx, 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 dx. Where does my path start? It starts at x equals 0. Where does my path end? It ends at x equals 0.02 meters. Can we evaluate this integral? Yes, we can. It's very easy. This is just a constant. So I'm going to get minus 100 nanocoulombs. It pops out front. Integral of dx is literally adding up the length of those steps. Well, dx integrates to x. So I could just literally understand what it means. I added length to steps. I get 0.02 meters. Or I can do it algebraically. 1 dx integrates to x between 0 and 0.02. Well, that's not difficult, is it? So I get minus 100 times 0.02. That's minus 2. It's in meters, so I get Newton meters per coulomb. It's the same as a volt. And then 0, this gives me 0. So I found my potential difference. Now, if you could calculate this going, say, diagonal, it's a good exercise to do. You need to understand how to evaluate this dot product here with the cosine of the angle between them, and it gets compensated by the length of the path. So I really invite you to do that. If you've seen path integrals before, definitely try this exercise to remind yourselves, evaluate the integral explicitly along a path like this. But hopefully, if you haven't seen that before, path integrals, what I did here makes sense to you, right? I chose a specific path, like a specific way up my hill, or down my hill in this case, to find the height difference. And I then was able to parameterize this path with my variable x. So I was able to explicitly write down an integral that I could evaluate. And I evaluated it, and I came to an answer. So this is just going to be volts. Here's my second example. This time we're going to go the other way. I imagine there's a voltage that's given to me. And it says the voltage at a position x. So imagine I put my x-axis. It could be negative 2. As I go along here, maybe there's 0 here. There's, 1, 2, 3, 4, so on. The voltage here and here and here and here, it's given by this function. 6 volts times e to the minus x over 5. This is something I picked as an example. I don't know what kind of distribution of charges caused this. What kind of source charges I had to put in places to make this happen. Probably some complicated setup. But I don't care. I'm given that this is the potential. Let's imagine someone's giving to you the shape of a hill that you have to hike up or down on. Right? I mean, it draws to you the profile of the hill, so you kind of know what shape it is. Where it's steep, where is it not steep? Well, it's given to us as a function. We're going to find the electric field at x equals 2. So electric field is a vector. In this case, it's all along the x-axis. There's no y nor z. the potential only depends on x. So really I'm just trying to find the x component. Right, it's the only component there is the electric field. I'll have a separate little video in which I talk about the electric field and potential in more than one dimension, so you can, sort of visualize what the electric field is in those cases. So the analogy with the hill works extremely well, as you will see. Right now we're working with this one. So, well, minus dv dx, right? X is my variable that's changing. I want the electric field in the x direction, so differentiate with respect to x. It's a function, I can differentiate it. Minus, let me write it out, ddx of 6 volts. I'm writing out volts to not confuse it with the V, times e to the minus x over 5 meters. Notice the thing in the exponent has to be just a number without units to make sense, so I had to just minus x wouldn't make sense unless you explicitly specify x given in meters or something like that. But I wrote it like this, x per 5 meters. Let's differentiate this. Well, this is a constant, 6 volts, times differentiating, I guess a minus sign. Differentiating this means, essentially by the chain rule, I have the thing that multiplies the x come out. I get minus 1 over 5 meters. And then the e stays the way it is because it's e to the something, right? We differentiate it, it doesn't change, just some prefactor comes out. And the prefactor is just the derivative of the thing in the exponential, the thing in the exponent. Okay, and that's it. So now we've got the electric field as a function of x, so in the x direction as a function of position x. Electric field in the x direction as a function of position x, the x component, right? Minus becomes plus, so I'm going up the hill, okay, so it points, positive, points to the right on my axis. 6 over 5, units is volts per meter, write that out, times e to the minus x over 5 meters, okay. So I want to find out the electric field at x equals 2, so I'm going to plug that in. And there's only the x component to worry about. It's going to be plus 6 over 5 times e to the minus 2 meters over 5 meters. Tiny little meters there. And the units is volts per meter. And if we evaluate that, unless I'm grossly mistaken, it comes to something like 0.8 volts per meter. Now you can see also explicitly why volts per meter is another unit of electric field. We worked out this way. It's the same as a Newton per Coulomb. Always check it. This is, right, a joule per Coulomb. Newton is a kilogram meter per second squared. You can make sure those units actually match by converting everything to kilograms and meters and coulombs and seconds. So make sure you actually do that at least once in your lifetime, so you can confirm that those two units are indeed the same. But got our answer. Alright, I leave it there. Hopefully you understand the basics of what potential is. You're going to get more of an intuition in the next video, where I try to show you what potential and electric field and so on looks like when you have more than one dimension. And we're going to be using that analogy with the climbing up and down a mountain a lot more. And that analogy is going to be helpful every time you think about potential energy, electric field, and so on and so forth. So I'll see you in the next video.